You want me to welcome everybody to Toronto, or no? You want to do it? Actually, you should do it. Take a celebrate.
I won't. I mean, I'll just say welcome.
Enjoy the weather. It's always like this. Or something.
I don't want to steal any jokes.
No, okay.
It was a shocking change.
Yes.
I can't really.
Yeah, well, it can get even more shocking. Once 1 year it went from 3 to 27 in 3 days. Like, yeah.
Where North Carolina, there were big shifts. Of course, the
much
whole
more
interval
early,
shifted
much
up,
more
but
early.
there were similar massive degree shifts, which would be make it very hard to dress in the winter. It would be very cold in the morning when I would go for school, but then during the day,
it heats up a lot. Yeah.
You brought us all in here very preemptively.
What does it work?
You brought us in preemptively. And we're just sitting here off.
It's good to build up attention.
Other one's like 1 minute behind.
It is.
That's the claim?
Yeah, it probably is. Yeah.
Oh, it's already 10.
Yeah.
Okay.
Yes, you see, we're already late.
Fine. All right. Well, welcome everybody to Toronto and the Fields Institute. We're happy to have you. And so we'll get the conference started with Spyros Alexakis, who will speak about the black hole uniqueness problem.
Okay, thank you, Yakov. I hope I'm heard. So thank you for the invitation to the organizers and to give the first lecture. Okay, so I'll speak about an old problem about I've been interested in a long time, and I would like to review some older and newer results. Okay, so the question of the black hole uniqueness problem. I'm speaking to relativists, but still, let me start with a very broad introduction. So the motivation for the problem is to understand the long-time behavior of black holes, in particular, the final state of evolving black holes in, let's say, zero cosmological constant. So more concretely, so let's assume we have an evolving black hole, and let's a priori assume that it remains regular for all time. So no singularities or anything in the exterior region. And we'd like to understand the asymptotics upon approach to time like infinity. Right? So to put it a bit in historical context, this is a sub-question of what was called in the 1970s by Penrose, I think, the establishment view on black hole evolution concerning dynamical spacetimes. So with zero cosmological constant. So the weak cosmic censorship asserts that any singularities that form in the spacetime will be shielded behind event horizons. And so the exterior regions, the expectation is when time goes to infinity, should settle down because whatever mass you have in gravitational energy will radiate off through the event horizon and to null infinity. And so it will settle down to some non-radiating final state. The expectation was that a non-radiating final state must be stationary. And so the question is, what are the stationary, the possible black holes that are stationary? Okay, so that's the broad historical context. All right, and to specify what I want to present today, I want to think about exclusive about vacuum black holes. All right, so in a space-time which is nice, so it's totally globally hyperbolic and has nice asymptotics of infinity, so an ADM mass and ADM angular momentum. All right, and so they're vacuum. And stationary, if you haven't seen it before, it means that there's a killing field, which at near space-like infinity needs to be time-like. Okay, in a neighborhood of spatial infinity is uniformly time-like. It exists throughout the space-time, but it's time-like near infinity, near space-like infinity. Okay, so some examples that I think most of us are familiar with. So the most classical one is the Schwarzschild solution, which is one of the first things we see when we study the subject. And so it is not only stationary, not only does it admit a killing field, which is time-like near spatial infinity, it's actually time-like throughout the exterior region. For all of r greater than 2m, it is time-like. And moreover, it is hypersurface orthogonal. So in Schwarzschild, you can split the time direction from the spatial direction and write the metric in this form. So what makes it stationary means that the coefficients don't depend on t. And this is the first example we see. The second example that many of us are familiar with is the Kerr family of solutions. So Schwarzschild was parameterized by one parameter, the total mass. And Kerr has two parameters, the total mass, which must be positive, and the angular momentum A, which must be less than or equal to m for the solution to be regular. So let me not write out the explicit form of the metric. I just want to say it is stationary. It admits a killing field, which is time-like in a region of space-like infinity, but it's not time-like everywhere. So in the exterior of the black hole, there exists a domain called the ergo region where this vector field is space-like. Okay? So these are the two main examples that have been written down of stationary black holes. So the question is, will these be the only ones? Are there others in addition to these? But let me start by noting, before we go to the question, that although you've only asked for one killing field, both of these examples, in fact, have many more symmetries. So Schwarzschild is spherically symmetric. So the degree of symmetry is the static killing field, in addition to all the rotations of the sphere, the three-dimensional space. And the Kerr solution, in addition to being stationary, to having this killing field T, has another one, which is an axial killing field. So there's another one killing field which generates rotation. So let's say the Kerr of some mass m and angular a has killing fields. Let's say dt and d phi. Okay, so this has orbits that flow to r, but phi has orbits that go from 0 to 2 pi. So they generate rotations. And to situate a bit better, if I were to mod out by the action of dt, I would have an initial data slice. So let's say if I take n Kerr and mod out by dt, the manifold you would have would be like R3 minus a ball. Okay, the ball corresponding, if you like, to the event horizon at time equals 0. And if you also mod it out by d phi, the quotient space would look like this. Okay, it's like taking R3 minus a ball and modding out by a rotation. Okay, so the region you're left with is an upper half space excluding a disk. And this corresponds to the black hole. Okay, so the two solutions that have been written down admit much more symmetry than you initially asked for. Okay, and the question of black hole uniqueness, are these the only ones? Okay, and so part of the interest in this is because it would provide a no-hair theorem, which would mean if these were the only ones, that would mean that the final states of evolving black holes are parameterized by a finite number of physical parameters. You know, the final state is given by the final mass and maybe the final angular momentum in vacuum. If you want to extend to electrovacuum, there would also be the total charge. We're not doing that here. And if you want to allow some gauge freedom, you can also include linear momentum, but that is not a gauge term. Okay. So this would be desirable and nice because the final states are just given by these basic physical quantities. Okay. And this we call the no-hair theorem. So hair would mean there's additional solutions beyond the ones we've written out. Okay. Okay, so let's start with some results in this direction. So the most classical result is due to Israel from 1967, and says if you ask for your black hole to be vacuum and static, not just stationary, then his celebrated theorem says that you must be the exterior of a Schwarzschild black hole. Okay. These classical theorems, okay, and there were some key steps somehow filled in by other people, but they go by these names usually, so I'm going to use these names. So for static, the result is very definite and very pleasing, and it goes back to Israel. In the stationary case, the classical theorem that we have is by Carter and Robinson. Okay, and it says that if you have a stationary black hole, which is vacuum, and in addition, you assume that it is axially symmetric, so it admits a rotation, right, in addition to just being stationary, then you must be the Kerr. So this is the most classical complementary result to Israel due to Carter and Robinson. The Carter-Robinson theorem has a very nice and interesting theory, somehow from elliptic PDE. So it wasn't understood by Carter and Robinson in those terms initially, but so Carter solved essentially the linearized. At some key step, he looked at the linearized version of the equation, and Robinson had a remarkable identity that proved the final step of uniqueness. Let me say a couple of words about it. So what it does is, if you have a stationary and axisymmetric solution, it turns out that the span of the two Killing fields is everywhere time-like. Okay, so morally, the equations in the presence of two Killing fields whose span is time-like become elliptic. The Einstein equations become elliptic, and in a suitable sense, you can reduce the equations to a harmonic map from this space into, so let's see if you've got a Robinson. Okay. So if you have dt and d phi present, then the vacuum Einstein equations reduce to a harmonic map. Okay, from this domain, okay, so from, if you like, the rotation of this around its axis into the hyperbolic two space. Okay. And the harmonic map also has some flexibility. You can change the gauge, if you like, and reduce, in fact, to a harmonic map from a very singular domain, which is not this. You can think of the domain here in R2 and perform the conformal transformation, like a Riemann mapping theorem, to bring it to the upper half space. But then this smooth metric, which had corners, becomes a non-smooth metric with two singularities here. And it becomes a harmonic map from this rotated around the axis into H2. And in a nutshell, the key for uniqueness is this harmonic map is mapped into a negatively curved space. And that's how the uniqueness is. That's the key to getting the uniqueness. This is a more modern understanding of the work of Carter and Robinson. Okay, so these are some classical results. Okay, but we do want to consider only stationary black holes. So the conjecture would be that if you have a stationary and vacuum black hole exterior with the horizon being non-degenerate, which excludes the extremal case, then the exterior region must be isometric to a Kerr solution. Okay, one of the Kerr solutions. Okay, so particularly, you don't need to impose axisymmetry. It should be true just with this assumption. So that's somehow the conjecture. Okay, so this result has been proven by it also is usually known as Hawking's theorem, but again, some key aspects were filled in later. Okay, and Hawking observed that it's true if the metric is a priori assumed to be analytic, real analytic, all the way up to and including the horizon. Okay, and the reason is Hawking's derived that if the horizon is genuinely rotating, then there exists a jet of a second Killing field on the horizon. Right? So that means a formal solution, like a formal power series, if you like, of a Killing field on the horizon, which solves the Killing equation to any order. Okay? So softly put, very, very morally, if you like, if the metric is real analytic, and if you have a formal solution to the Killing equation is overdetermined, and you can actually extend to a real solution. It becomes a real Killing field if you were analytic, if the metric was analytic. Okay. So, okay, and if you can do this, then you fulfill the assumption of Carter-Robinson. So your spacetime was not just stationary, it was also axisymmetric. And so Carter-Robinson applies, and you know that you must be Kerr. So that was some other classical state of black hole uniqueness, the classical Noether theorem, under the assumption of being analytic. Okay. Now, you could, as in Carter-Robinson, if your Killing field had been time-like, Okay, then indeed, in the presence of a time-like killing field, the Einstein equation is reduced to an elliptic problem, and you get analyticity of the metric for free. The trouble is that in the Kerr solution, the ergo region is unavoidable, and so there's some region here where the killing field is not time-like; it must be space-like, and so there's just no a priori reason why it should be analytic. Okay? So that's why it's an undesirable assumption. It's a genuine extra assumption. And I suppose, as we all know, when we do analysis in spacetimes, we don't work in the analytic class because morally it's right. It's if space-time metric is real analytic, then if you know it in an open neighborhood, you know everything about the history of the universe to the future and to the past, and that's not a physically reasonable assumption. Okay, so analyticity is not a desirable assumption. Okay, so these were the classical results. So let me start with now more modern results, going back to papers of Ionescu and Kleinemann from 2008. Okay. So they considered the same setting, so a stationary vacuum black hole exterior, okay, connected with one black hole, regular and non-degenerate. Okay, so then they replaced analyticity by an additional assumption, which was that a natural tensor that I don't quite want to define, something that you can make sense of in any stationary spacetime is naturally defined, that vanishes on the horizon. A certain natural tensor. It's the curvature tensor plus something built out of the stationary killing field. Okay. So you're putting a condition exclusive on the horizon of some function being zero, if you like, or some set of functions being zero via this vanishing of this tensor. And this tensor is the one that perfectly characterizes Kerr. Okay? If you're in an open neighborhood, this tensor is zero, then you're isometric to Kerr. Okay? So they impose this condition exclusive in the horizon, and they derive that then you should be isometric to the Kerr solution after some cover or something. Anyway. Okay, so this was an important extension, right? Because it gets rid of the assumption of analyticity. It does impose this condition on the horizon. But also, I want to stress it was the first to introduce the concept of unique continuation in this circle of questions. Okay? So I will return to unique continuation later, but for now, let me just say this. Okay, so there's some more results later on with me, with Alex and Sergio that I'd like to review. So we use unique continuation in a new way. And there are three results that I'll just synopsize in one theorem here, but I'll go over them a little bit quickly, and maybe I'll say something more later. Okay, so if you have a stationary and vacuum black hole and the event horizon is regular and non-degenerate, then result number one was this formal jet of a second killing field, this formal solution to the killing equation, really does extend to a genuine killing field in some open neighborhood, right? So the idea would be if I draw a 2+1 picture, actually, so let's do. Okay. Then there is a region where you can extend the killing field like this. Okay. Into such a region. If I do a 2+1, this was 1+1. So let's kill one dimension and let's represent the event horizon, right? The future and the past event horizon that intersect transversely at 1 S2. So this is meant to be thought of as 2. Okay. Then the extension of the killing field is in some region like this. You can imagine some warped hyperboloids, which are rotated around the event horizon. Okay, this is the first region of extension. Okay, so this was so this doesn't suffice to conclude it extends beyond, right? Because you can still be stuck in the ergo region. Remember, so there's the ergo region here. Now, if I were to draw this first region of extension there, it will be something like this. Okay. Okay. But the ergo region is big, and so you can, right, there could be area left, and so you can't conclude by this extension. Okay, we had a second result, however, which says if you a priori assume that your space-time is C2 close to the Kerr family, to a member of the Kerr family. Okay, so the entire stationary space-time is a priori assumed to be C2 close in a certain weighted sense to the Kerr family. Then this Z that you extended only here can be extended throughout, everywhere. Okay, and so then, right, we have Carter-Robinson at our disposal. So that was the second result. And there's a third result. These are three separate results, really. So if you assume instead of C2 closeness that your rotational killing field was small on the horizon, or in fact that some the angular momentum measured at infinity is small relative to the mass, okay, then you can also extend everywhere. The little observation there is that the size of the ergo region, at least in Schwarzschild, is determined, or let's just say the size of the ergo region is determined by the size of Z. If your Z is very small, the ergo region will be smaller, and the size of the orange region is somehow linked to the mass. Right? So if you take the angular momentum very small, you have this first region of extension, it's contained inside the orange one. So already your theorem 1 was sufficient, and you got your killing field out. So results 2 and 3 are global theorems. They establish black hole uniqueness because you can appeal to Carter-Robinson. But their assumptions are genuinely different. Okay? The reasons why they hold are genuinely different. One worked in the perturbative regime. If you a priori assume you're close to Kerr. The other one was you don't a priori assume that. You just assume that your rotation is very small. Okay, so this was these are the results. All of these followed by unique continuation, and I would like to discuss a little bit unique continuation for waiver questions. Okay. Yes, yeah.
Do you have that vanishing of the tensor?
No, you do not. Yeah, all these do not have the vanishing of the tensor. Right? So, so both these are open classes of stationary spacetimes. Okay, whereas imposing and vanishing is not an open class; it's in codimension. Yeah.
So in the result 3,
yeah.
So you're assuming something about the axisymmetric on the event horizon, and then you have to show that implies that ergo is small.
Yes. Yes. Relative to the orange region, relative to the region where you could extend by virtue of result 1. Yes. So the non-degeneracy helps you because you become time-like pretty quickly. That's the idea, if you like. Okay. So all of these, the last 3 that I showed, and the old Bayes can claim on their own, use the technique of unique continuation. I'd like to take some minutes and discuss that. Okay, so unique continuation is a very, very old subject. It doesn't have to do with relativity or anything like that. It goes back to basic PDEs. The most classical result is due to Holmgren in 1901. Okay, so it's for a very general class of operators. Let's just do it for wave operators now. Okay, so consider a linear wave operator. It has to be linear. Okay, so here we are of order 2, and assume that the coefficients are analytic everywhere. So the question is, if you have a function that satisfies the corresponding PDE, and your function vanishes in some set, must it continue to vanish elsewhere? Okay, so let's say, unique continuation is if you have a solution of a PDE, P of phi equals 0, and let's say phi is identically equal to 0, in some domain, in some omega inside Rn+1, open. Does that imply that phi must be 0 everywhere? Okay. So Holmgren's theorem, and in fact all the unique continuation theorems, essentially become local results about a hypersurface. Okay, so let's think that our domain omega admits a hypersurface that divides it in 2 parts. The sigma minus is here, and sigma plus is there. Okay. So locally, right, the hypersurface divides the space in 2 parts. And let's suppose, okay. So the typical result was if you vanish on one side of the hypersurface, must you vanish on the other, at least locally? Must you continue to be 0 on the other side? So uniqueness for PDEs. Okay. So Holmgren doesn't actually pay attention. He just looks at the hypersurface itself and says, if you have that the function vanishes in the hypersurface and its derivative vanishes in the hypersurface, if it's a second order operator and it's a non-characteristic hypersurface, then formally you can determine that all the Taylor coefficients vanish. But you weren't a priori assuming the solution is analytic, right? You can say all the Taylor expansion entirely vanishes, but you're not assuming it's analytic. Nonetheless, if the coefficients were analytic, you know the solution must be 0 in an open neighborhood of that hypersurface. Okay? So very, very classical analysis. That applies to linear wave operators with a priori analytic coefficients. Okay, so the result, the version of unique integration that we use is due to Hormander. And it considers a second order operator with some, let's say, so box G being the principal symbol. And it looks at extending just locally around 1 point P. Okay, and the Hormander condition is if the domain in which you know you're 0 is pseudo-convex, then you can extend beyond. So pseudo-convex means the following thing. Consider it means convexity with respect to null vectors. Okay, so convexity, full convexity would mean take any tangent vector, right, and shoot the corresponding GD6. You want it to lie on the sigma minus side. Okay, the region into which you want to push into should be should have this property that the null the GD6 lie on the other side. Okay, so full convexity, right? So what does it mean that the sphere is convex? It means that if I take a point and I shoot the corresponding GD6, they lie outside my sphere. If I'm trying to push into a region, well, I want it to be convex, meaning that the GDs that are tangent to the boundary lie outside the domain into which I'm trying to push. Okay, does that make sense? So this is the okay. So that's what convexity is. A reminder of what convexity is. Pseudo-convexity means you don't need to worry about all GD6. You just need to worry about the null ones. Take the null GD6, consider the corresponding, right, the extended GD6 locally. It needs to lie on the side where you know you're 0. So phi was identically 0 here. And here is phi identically here, question mark. Okay, so if you have the pseudo-convexity, then yes. Okay, so Hormander has proven this by Carleman estimates. Right? So another a type of weighted estimates for wave operators. So the Hormander result is a local result. It's around each point. So if you have a hypersurface and you have convexity around 1 point, then a function that solves the PDE on one side must extend to the other. Now, you can upgrade it to a more global result, assuming that, assuming that there is a function, let's say, whose leaves are all pseudo-convex. So very concretely, if you had one surface sigma, you can always think of this as a level set of a function, and you can maybe ask for a function whose remaining level sets. Right? This is f equals 0, this is f equals 1, this is f equals 2. Okay, all of them are pseudo-convex. Assume you had such a function. Then if you knew that you're initially 0 here, you can keep on applying Hormander's theorem and derive your 0 all along wherever this function exists. Okay? By just applying the result, the local result, over and over and over again. So if you can construct such a convex foliation, pseudo-convex foliation, you can extend all the way as long as that foliation exists. Okay. Okay. So the result too that I said, also the Ionescu-Kleinman result and this result, essentially constructed such a function in the Blackhole theory. Let me say something about the technique there. So one key realization, of our joint work, was that this technique that normally is used for functions, right, to prove if a function is 0 on one side, then the function must also be 0 on the other, to apply to extension of killing fields. Okay, it's not obvious, but we derived it's true. Right? So yes. No. Yeah, of course, he does not assume analysis. That's right, just a C2 metric. Yeah. That's the whole point. Thank you. Okay, so one observation of us, let's say if you is if you have a solution to the vacuum Einstein equation, reach your G equals 0. Okay. and you have a killing field T in sigma minus, okay, then that vector field extends to the other side, remaining killing. Okay, so that symmetry of the equation extends on the other side. Right? So it was in a unique continuation for metrics, in fact, for symmetry of the metrics. Okay. So let's say this, provided you have this condition, you have this pseudo-convexity. Okay, and in fact, if you don't have any metric, but you have a metric which you already know is stationary, then you don't need to check the full Hormander condition. You don't need to check convexity with respect to all null GD6. You only need to check it with respect to the ones that are normal to T. So if sigma is pseudo-convex with respect to null vectors with which are normal to T, then the killing field extends. In fact, in black holes, it is unavoidable that convexity would fail. The full null convexity would fail somewhere, right? Because of trapping. You can even see it in Schwarzschild. Okay, so if you take R equals 3m, there are null GD6 that stay at R equals 3m. So you could never imagine a function whose leaves will come and then first start from the horizon and go and first touch R equals 3m. You cannot do that. Right? The convexity will fail. If the moment you touch, then that surface couldn't have been convex. But the point is, you don't need to check all the null directions, you just need the ones that are normal to T. So in Schwarzschild, you're in fantastically good shape because T is time-like, so no null direction is normal to T. So it's always, you're always going to have it. And if you're specifically Kerr, this turns out to be true. So the trapped GD6 are never normal to T. That was a certain angular moment. Okay, so that was the one key element of the proof. Okay. Okay, and now, for example, in the original Ionesco-Kleinman approach, and also in the perturber result we then construct a global foliation, foliation by level sets of a function, which are globally pseudo-convex, like T normal pseudo-convex. Okay. And if you were exactly Kerr, they figured out what function to choose. If you're close to Kerr, then a modification, basically that function continues to hold. Convexity is an open condition, so that property continues to hold. Okay, so these were the older results. So I'd like to move on a bit to the new results. So the main difficulty is, as we said, to extend the killing field in the ergo region, where the T is space-like. Right? And that ergo region could be pretty large. Okay? So already in Kerr with large angular momentum, it is rather large. Okay, so if we think a little bit on our own, maybe loosely, how could it, if it were true beyond these settings, how could you try to approach it? So let me propose three possible avenues. Okay, so the one is some sort of magical version of Holmgren's theorem, the very classical theorem, right? Which would apply to nonlinear equations, perhaps, right? The Einstein equations are nonlinear, but somehow if you just write out the Einstein equations, right, the coefficients are analytic, right? The unknown is G, the metric is G again, so you might think that somehow it's a nonlinear, right? But analytic coefficient, right? Because all the coefficients are like constant numbers, and then it's just the unknown and derivative of the unknown. This seems very, very, the Holmgren result really needs linear, and okay, there are many, many difficulties here. The second avenue you could hope for is that there do exist pseudo-convex foliations. These T normal pseudo-convex foliation does exist. Somehow you can find it. Somewhere it's around, and you have to find it. You're not going to be close to Kerr. You can't use any properties of Kerr, but somehow they exist. And the third would be, well, maybe you can do without actually extending and getting a full second killing field. Maybe you could get something that is partially killing, and then you won't have Carter-Robinson, but maybe you can reduce to some sort of weaker form of Carter-Robinson. Okay. In fact, if you think about it, the only region you're trying to get is this one here. You could think, if I've already extended in a little bit outside the horizon, maybe by by analyticity, the killing field is extended everywhere. There's some small island. How bad can this island be? Maybe if I if I don't have the killing field, but something almost like a killing field in the remaining region, maybe some modification of Carter-Robinson could maybe suffice. Okay, so these are three avenues you could try to take. Okay, so it's number 2. Okay, so I want to motivate, I haven't presented the result, but let me motivate it by some other results with me, with Ali Mohammadi, who's in the audience, and Larry Oksanen, in a completely different subject. Okay, but again, we use unique continuation. I wanted to use this a bit as inspiration. Okay, so let's say you're interested in unique continuation from a null cone in a Lorentzian manifold. So we're not doing Einstein's equations anymore. You've just got a Lorentzian manifold, and you have a solution to a wave equation, perhaps. And you would like to say that if your solution is 0 inside the null cone, or even just on the null cone, but the high order, maybe it's true away from it. Okay, so you would like a foliation that starts from, let's say, so sorry, I said it in reverse. So you're maybe 0 in a cylinder that cuts the null cone on the outside, and you want to extend all the way inward into the null cone. Okay? Now, convexity has something to do with the sign of curvature. So there are some results that we have, which is a unique continuation result, and establish the following. If you have a wave equation, box G of phi plus maybe a lower order term of V phi equals 0, and you know that your phi and your d phi are 0 on a cylinder, which cuts your cone, and you would like to extend all the way inward into the cone, you would want to construct a convex foliation, a pseudo-convex foliation that goes into the cone. And how would you find it? So we observed that if you have a certain sign of curvature, then the most natural thing is to do the distance function, right? The Lorentzian distance function from the tip of the cone. So the result is, consider the space-like vectors, okay? And so consider the space-like distance from the tip of the cone. If you were Minkowski, these would be hyperboloids, one-sheeted hyperboloids. If you're in general Lorentz symmetric, there's something like hyperboloids, and they're rotation symmetric. They look like this. Okay. So the idea was, under a certain sign of curvature, if the curvature is negative in this sense, so put in 2 null vectors and put in 2 space-like vectors that are normal to the null. So some sort of null sectional curvature. If this is negative, then the foliation you can construct by distance function starts being convex in a favorable way to go from outside inward. Okay. So that was a result. Okay. So the favorable sign, when you have negative curvature, it allows you to go from outside inside. Okay. The foliation you get by just looking at the distance function. Okay. Okay. So when we had to assume a few things, for example, you can form focal points. You can, the levels that the distance function can break down pretty badly. We assume that doesn't happen. Okay. All right. Okay. So this was the result. So I want to display some hidden pseudo-convexity inside the Einstein equations, okay, inspired by that old result. Okay. So to introduce them, I want to consider the reduced Einstein equations. So if you have a stationary space-time, you can mod out. So reduced Einstein equations. Okay. So if you have a 3 plus 1, everything I'm saying is 3 plus 1 strictly. Okay, 3 plus 1. And you have a killing field T. You can mod out by the action of T. Okay, and you get a manifold of dimension 1 lower. And to speak of a metric, let's do that exclusively in the Ergo region, wherever T was space-like. So you mod out. Okay, and you obtain a metric on the product, on the reduced space, which is 2 plus 1. The metric H tilde is still a Lorentzian metric, and somehow just projection to the space normal to T. Okay, okay. So that's the first projected metric. The projected equations usually do a conformal transformation. You take the magnitude of the killing vector, all right, and you construct the new metric H by multiplying H tilde by this X. All right, so you obtain a system of equations, but let me highlight one for them. The Ricci tensor of the new metric has this form, all right? So it is the gradient of x times the gradient of x with itself. You're dividing by x squared, and there's a one form that I don't want to get into. Okay, let me not say what it is. It's just a particular one form. You build it out of x. Okay, so it has this form. So it's like a source for the Ricci tensor. Okay. So one small thing to observe. It's a little exercise. If you had in this metric, in the projected metric, if you take any null vector and look at the essentially unique space-like vector that's normal to it, then you have this sign for the full curvature tensor. This has to do with the Ricci curvature in 2+1 characterizing the full curvature tensor. Okay, so you obtain this requirement. This is the opposite sign than what we had with Ali and Larry Oksanen, right? But it will be helpful to extend from inside out, which is what you want to be doing in this problem. You want to start from inside near the horizon, keep extending outward. Okay? So it gives us an idea on how to do it. Okay, so let me discuss a little bit how you could do it. So one observation is I've been saying you only care about T-normal pseudo-convexity. When you go to the projected picture, right, the T has disappeared. So if you were pseudo-convex in the projected picture, your T-normal pseudo-convex in the lifted picture, in the original picture. So that's good to have. Okay, and so it suggests you want to work in the projected picture exclusively inside the ergo region. Okay, and it gives us a hint how you should try to find your distance. The function whose level z will always be pseudo-convex. Maybe you should be inspired by this work and try a distance function. Okay, so this is the result. So the result is that under the usual assumptions, right, that you have a vacuum stationary black hole, which is regular and sub-extremal, so non-degenerate. Then I need two assumptions, which I view as soft. One is I need the ergo region to be simply connected. It could be arbitrarily large, but simply connected. And for somewhat technical reasons, I need this magnitude of t, this GTT, exactly when it's 0. D of that should be non-zero. Okay, so that's a known, right? So that's a more technical condition. Then the space-time is a symmetric to curve. Okay, so let me try to present something. And the way it works is the second killing field extends throughout the ergo region. So you can extend the killing field to the entire ergo region, and then you will appeal to Carter-Robbins. Okay? Once you've swept out the entire ergo region, you can cover the rest immediately in one go, and then you can appeal to Carter-Robbins. Okay, so let me discuss. Let me try to draw some picture here, maybe. So the most somehow optimistic scenario would be, let's say, work like here. Just take the distance function from a specific cone, actually better from a specific hypersurface you already know to have. For example, this last one you got here, the last red one, right? And you can keep extending outside by maybe just the space-like distance function. Okay, there's two obstacles here. One is if you, let's maybe draw this picture. And you have, you have an ergo region, which a priori might have been huge. And you have an initial region where you've already extended and you want to keep going. All right, so you might think, take somehow the distance function from this original surface, and maybe that will provide, right, that will eventually, maybe like in Lorentzian space, if you look at the distance, in Minkowski space, if you look at the distance function, you can go arbitrarily far. And if these level sets were smooth, then you'll be in great shape. So problem number one is the distance function can cease to be smooth. Okay, you can have caustics, and so the level sets of the distance function could look like this. Right? So you can form caustics. So due to caustics, you can get surfaces which are no longer convex. So that's one difficulty. They can have things breaking down. Nonetheless, the claim is you can automatically extend to a region, always, even if this happens, you can automatically extend to a region which is comparable, measured with respect to the metric h to the radius of injectivity, even if this happens. Okay, so I can keep on extending to regions of size which are bounded below, right? And I can construct it by looking at distance functions from curves. Okay, and even if this happens, I can continue on extending. Okay, the thing is, I remind this the size of these regions is 1/10, let's say, of the radius of injectivity of this metric h. Okay, okay. Now. The second difficulty, and this is rather severe, is how do you get a global, right? You're saying even if the level sets of the distance function break down, they cease being smooth, you could keep on going, fine. Maybe you could say, I'll keep on shooting I'll just shoot GD6 and they'll go arbitrarily far. They will reach the boundary because that's the intuition from Minkowski space, right? Or from Lorentzian manifolds, right? So if you shoot out space like GD6, they do get very, very far as you like. You can reach the tip of a point from point space like separated by some space like GD6. So here comes the second difficulty. In this picture, the metric you've constructed is extremely badly singular at the boundary of the ergo region. Okay? So a consequence of this is that the space like GD6 you want to work with will not get to the boundary of the ergo region. All of them, possibly maybe except for 1 or 2, will go and return. Okay, so this is a feature of the singularity of the metric at this hypersurface. Okay, and if you like geometric analogs, this already happens if you take a Riemannian cone, like just a Riemannian cone, and you take, right, so you take a curve, and you try to shoot the unit normal to the curve, right? These GD6, right, do not reach the tip of the cone, right? The huge majority of these GD6 will turn around. Okay? So something very similar happens here. The GD6 will not get close to the boundary of the ergo region. In fact, you'll be left far from it. Okay, so the technique is some sort of a nested extension. So what you can prove is for any point strictly in the interior of the ergo region, you can construct a finite number of local extensions that will reach that point. Okay? For each point strictly away, there's a finite number of extensions that gets to it by these two soft assumptions I said. All right, and so once you have that, then by continuity, you can reach the boundary of the ergo region. And then from there, you can extend everywhere. Okay? And so by Carter-Robinson, you're basically done. Okay. All right, so I tried to give an overview of the main technique. Okay, the key feature is that once you start with a curve which is pseudo-convex, the level sets of the distance function, right, will maintain the pseudo-convexity as long as they are wherever they remain smooth, and even in points where they don't remain smooth. Okay, so that's what I wanted to say about this this technique. Let me maybe close with a couple of comments. This should be an applicable technique for just extension of Killing fields, not just black hole uniqueness, but in fact, right, but in this notion, if you have a black hole space-time and you have it stationary and you want to extend Killing fields even in the presence of matter, one expects this should be applicable. So the convexity we got from the sign of curvature, right, this one here that stems from this inequality, one expects should get even more terms that make it even more favorable, even more positive. Okay. So without matter, there is no Carter-Robinson theorem in general. Okay, and so one can only get so far. But I do believe it'll be a useful technique beyond the setting of vacuum equations for extending the second Killing field at least. Okay. All right, and with that, I'll stop here.